Hi, my name is Jessica Zhang, and I go to proof school in San Francisco, California. My research was about contact structures on a solid torus. So what is a contact structure? A contact structure is just a special geometric structure that we can define on any three-dimensional shape. In particular, what it does is it attaches a plane, so like a sheet of paper, to every single point of our three-dimensional shape in such a way that no surface is everywhere tangent to those planes. So intuitively, a contact structure is just a really twisty way to attach sheets of paper to every single point of our three-dimensional shape. And now I was looking at contact structures on the solid torus. A solid torus is just a donut. And the reason we say solid torus is because we want to emphasize that we're including the interior of the torus and not just the boundary. So my research question was really about classification of contact structures. So we got to talk a little bit about how are they classified. So what are we sort of basing this classification on? And what we're basing the classification on is the behavior near the boundary. So on any three-dimensional shape with boundary, the classification of contact structures boils down to a classification based on how they behave on the boundary. And this behavior is determined by a special set of curves known as the dividing set. These are some curves on the boundary, and they're going to sort of define how the entire contact structure behaves on the boundary. In the case of a solid torus, it's been shown that the dividing set can only take on certain specific forms, and in particular, it's always going to look like an even number of parallel curves. So this sort of means that we can parameterize or just write a dividing set as three numbers, n, p, and q. So 2n is the number of components, so the number of curves, and then p and q represent the slope of each curve. Because again, these are parallel curves, so they have the same slope. So basically, my research question was, given n, p, and q, how many contact structures have the dividing set n, p, q? So before we get too far into that, I do want to address the fact that my research says classification of tight contact structures, and I haven't talked about what tight means yet. Basically, contact structures can be split up into tight and over-twisted. And the reason I'm focusing on tight ones is because over-twisted contact structures have already been fully classified. So actually, most research nowadays about the classification of contact structures is going to be about tight contact structures. So that's what tight means here. It's just a specific kind of contact structure. So on the solid torus, there are some known results. Basically, they are for specific cases of dividing sets. And therefore, when n equals 1, so when there's two components, and when p and q are both 1, so when the slope is just 1, basically. So there's two known results, and what I did in my research was I took those results and I used them to find the full classification for any n, p, and q. Now, the way I did this was by using something called a bypass. A bypass is just a half disk that we can attach to any shape really, but what it does is it's going to change the contact structure of the shape, and it's not going to affect the topology. So it's not going to change what the shape is. It's just going to simplify our contact structure for us. And so in particular, on the solid torus, it's actually going to simplify the dividing set. What it's going to do is it's going to take npq, or we actually say n minus pq for, I guess, it's just convention, but it's going to take n minus pq to n minus 1 minus pq. So you can already see how it's going to simplify down to n equals 1. And I'll do something kind of funny when n equals 1, but that's not really a big deal. But the primary idea is that a bypass is going to simplify the contact structure on the solid torus. So this stuff was actually all known before I started my research, but what I really did was I showed that you can actually use that fact in order to go from the simpler cases in order to go back to the more complex ones. So basically what I showed was that you can sort of reverse this. You can take the known results and you can build off of those by attaching bypasses to the outside, and that would sort of reverse the interior bypass operation in such a way that would let us sort of inductively find the number of tight contact structures on n minus pq for general n, p, and q. So that was my research, and in the end I did come up with a closed form formula for that. So yeah, thank you very much for watching this.